Tuesday, 25th of February at 10 a.m. Eastern Time, our Optica corporate members meet to discuss how to collaborate on PIC packaging and test. The goal is to answer the Optica question: what can you do for them and what can they do for you? Photonic Integrated Circuits, or PICs, are at the core of modern optical modules. However, one of the biggest challenges for the industry is how to efficiently package and test at a scale that meets the growing demands from the coming AR/VR, AI, Medtech, and consumer trends. In this meeting, we will explore the transformation of PIC packaging and volume manufacturing, drawing parallels to the well-established CMOS microelectronics industry. Our discussion will focus on critical challenges such as precision alignment, thermal management, and co-packaging with electronic components. This discussion will be led by Peter O'Brien, the director of PICSAP, the Photonic Packaging Pilot Line at Tyndall National Institute, Nick Salia, principal engineer at Intel, Jeroen Daus, the CTO of FiC Photonics Assembly, and Leili Shiraming, the program manager for Silicon Photonics at IMEC. They will be joined by the rest of our corporate members in what I anticipate will be a very active Zoom room. Join us live on Zoom or follow the discussion in YouTube. If you're not yet an optical corporate member, now it is the time to become part of the most active and engaged community in the photonics. Together, we shape the future of our industry.
Good morning, afternoon, evening, everybody, wherever you are in the world. My name is John Pugh. I'm the Director of PIC and Quantum Technologies at Optica. Welcome to the online industry meeting for PIC packaging for volume production. We have many system integrators and enablers in the room here. As you can see on the left, we have talks from Tyndall, Intel, CITC, FiC, Sumitomo, and IMEC, and then enablers coming in to talk about where their enabling technologies can help the system integrators. We have sponsors for the meeting, many sponsors for this very popular meeting: New Photonics, OpenLight, FiC, FineTech, Quantifi Photonics, PIC Advanced, Conscient, and Vanguard Automation. Thank you for your sponsorship and support to the meeting. We have a series of upcoming online industry meetings this year. We have today, and in a week's time, we have OLEDs and micro LEDs, and you can see the list coming up over the coming year. Please join us for those meetings. So the Optica corporate membership is a global trusted network. We have market reports, year-round events, the OIMs, and also in-person summits where we facilitate networking between companies. We have substantial discounts to our events and some other events. We promote your achievements as companies and many other engagement opportunities. So download all the Optica industry content here on the QR code. We have the market reports, presentations from these meetings, videos, tutorial, and roadmaps, and much, much more. So advancements in photonic integrated circuit packaging for volume production has been accelerating, driven primarily by the demand for high performance, cost-effective solutions in data centers, but other applications in telecommunications, LiDAR, biosensing, and quantum computing are becoming much more prominent. Key developments and topics that will be discussed today include heterogeneous integration, advanced packaging techniques, improved fiber coupling methods, standardization and automation, and also cost reduction strategies. I'd like to thank in advance all our speakers for joining this meeting today and being prepared to answer your questions. We're thrilled to welcome back the first speaker of the meeting, Peter O'Brien, Director of Photonics Packaging Pilot Line at Tyndall National Institute in Cork. Peter, with the announcement of the €400 million CHIPS JU PIC Pilot Line, PICS Europe, can you give us an update on how you'll bring Tyndall's advanced packaging expertise to help the pilot line build the future technology supply chain?
So I was going to talk very briefly about two things, and of course one of them is PICS Europe, but I was going to keep the best thing for last. Just very, very briefly, kind of what we're doing in PICS Europe. I'll speak a little bit about that. And my first one or two slides is kind of speaking towards that, because it's really interesting kind of trends we're beginning to see. So, you know, you might have seen me present this slide before where, there's a lot of intricacies in photonic and electronic packaging. So we need to consider electronics when we're packaging these components. So there's a lot there. And we see very complex chips. So for example, this is a very large chip we're working on, and you can see this type of package, very, very large. It's not unique. So there's a big push now towards very advanced, very complex, extreme packages, let's call it that, moving away from the gold box. So this is really kind of a very important trend. So where we see, historically we had the butterfly package or kind of variations of that, maybe more custom. What we're seeing and what we're doing in PICS Europe to a large degree is kind of linking in with the big development towards chiplet style packaging. So in the electronics world, where we're breaking up the chips from very large, high-end, potentially low-yielding foundry processes to chiplets and integrating them onto substrates, so interposers. So for example, having silicon or glass interposers. And then what's really important is that the packages then are looking more like an electronic style package. So like a ball grid array, BGA style package. So this is a very important trend. It's kind of driving applications like in co-packaged optics, but we see it in other areas as well. And a fantastic development here is we're starting to see an alignment of photonics packaging with electronics packaging. So for example, in AI, where photonics is being integrated into the chip to bring more efficient and high bandwidth data to the edge of the chip. So this is work we've done recently, presented at OFC not so long ago. This is with Intel and Altera, packaging very large electrical chips like an FPGA with photonic and electronic chips and bringing optical fibers onto that package. So again, it speaks to this kind of chiplet style packaging. And to kind of support that, we have other projects, for example, where we're using glass platforms. So using glass as an electrical interposer. So flip chipping components. In this case, it's an indium phosphide PIC, but with micro-optics for out-of-plane optical coupling. And obviously, in a pilot line, it enables you to develop the equipment and all the necessary materials to be able to develop such a type solution. So again, these types of electronic style packaging processes, interposers, chiplets, electrical integration, and BGA packages, we're seeing a very strong trend there. So John, you asked me to speak very briefly about PICS Europe. This is a major investment by the European Commission as part of the CHIPS JU, the CHIPS Joint Undertaking. It's one of 5 pilot lines. So CPL 5 as we call it. And essentially what we're doing here is PICS app was a standalone packaging pilot line. The fantastic thing about PICS Europe is we're bringing all parts of the ecosystem. So design, chips, integration, packaging, of course, test and reliability, developing systems and training, and operations to enable users to access those facilities. So just very briefly, you can see the list of partners here. So the coordinator is IXFO in Spain, and Tyndall, for example, will be leading the packaging activities. We have the Netherlands, Belgium, Poland, United Kingdom, France, Austria, Italy, Finland, and Portugal. All play a very important role, for example, in developing the chips, some major foundries. And a key part of this, I can't emphasize this enough, we want to work with industry. So as soon as we can, we want to engage with industry. The plan is we start very soon, potentially in May, possibly June, and we will open our doors and start to work on developing these more advanced packaging solutions. And we want and we need to work with industry. A key enabler to enable users to engage with the pilot line. We've developed these packaging design rules, ADKs, assembly design kits. These will be closely linked with process design kits coming out of the foundry and test design kits. And then that's really the interface. So the users will use these design rules to interface with the chip, the packaging, and the test. So really what we're hoping is that we can offer a single point, entry point to a very wide ecosystem across Europe. And I think this is a manufacturing production ecosystem. And as I say, I can't emphasize enough, it's very important we work with our industry partners so we can transfer these processes and enable them to scale. So again, a key part of this is our gateway. We had the PICs app gateway at Tyndall. We will also have a PICs Europe gateway. This will be managed by our partner EXFO in Spain. Again, following all these standardized packaging, chip and test design rules. And that's really the way to engage. And as we develop those processes, we will transfer those to our industrial partners. So one message I want to give today, if companies are interested in working with us and being part of this scale-up opportunity, please do not hesitate to contact me or Valerio in EXFO. So we have a number of partners that, maybe locally you can contact, but maybe as a first point of call, contact me. Very happy to talk to you, because this is really an important part of our pilot line, scaling up with industry. Just very briefly, my last slide. What is the timeline? So the pilot line funded, the grant period runs for 5 years, but of course we're looking well beyond that. So we're developing things up, but very soon we want to engage. So working with industry, this is basically working with our industry partners to scale things up. That'll happen almost immediately. We need to speak to you so we can kind of align with what we're doing, with what you can offer us, and then slowly open our doors halfway through the project, but possibly sooner if we can do that, to work with you to offer these services to the many people that need them. So John, that's a quick summary of PICs Europe and what we're doing, some interesting developments in the field of photonic electronic packaging. Thanks.
Peter O'Brien, congratulations. Congratulations on what you are achieving. This is great. I'm ecstatic. We want to make sure that that Europe gets the right position with this pilot line, and the work that you and many other institutes have done over the last 12 months, and especially during last summer, is paid off. So on behalf of Optica and the whole network, congratulations. We have a lot of questions for you, but I will summarize them into one. You keep proposing glass as the right substrate for photonic integration. And one comment in the chat is that it is a poor thermal conductor and is not quite CTE compatible with silicon photonics. How do you address this when actually there's a stress coming from a BGA package?
Sure, it's a very interesting point. So I mentioned glass, but we're not only looking at glass. We are looking at organic, we're looking at ceramic, and we're looking at silicon. But a very nice feature of glass is, well, there is a very good CTE match. It's very good at high frequency. A key point here is we can integrate optics into the glass. I know, for example, Intel have been working on that very successfully. But glass also is being used in the semiconductor electronics industry for panel. So you can make large scale panel electrical interposers. So it's becoming an established technology in the electronics world. We want to also leverage that capability. So there are benefits to glass, but I want to emphasize we're looking beyond glass. I mentioned glass, but there's real opportunities to bring that technology into the photonics electronics packaging world.
I can't agree more with you, and I'm a huge fan of glass, and using glass for photonic packaging has dramatically reduced the cost and also facilitate the fiber-to-chip coupling. So there are many advantages on this. Point to glass. One company that you have been in touch with is the company FemtoPrint. It is great to have Rolando Ferrini with us today. Rolando, you joined this meeting and you just heard from Peter O'Brien what is this goal of this pilot line. I'm pretty sure you're excited. You know very well what a pilot line is. Tell us what you bring to the table.
Thank you, Jose, for the nice introduction. And yes, I know what a pilot lines are. One of them in my past. So congratulations to Peter for getting this pilot line that will have impact in Europe. So today I'm here for a 2-minute pitch to present what FemtoPrint can offer in terms of glass microcomponents for fiber connectivity and integrated photonics. First of all, let me introduce FemtoPrint in 1 second. FemtoPrint is an SME in Switzerland, existing since more than 10 years, 40 people, 2 sites in Switzerland, 1 office in the US, and we are specialized in laser micromachining of glass microcomponents, serving several markets, going from watchmaking to life science, medical, quantum, and optics and photonics. And in optics and photonics, we focus on fiber-to-chip connectivity. So we offer components and systems and glass components and glass systems to serve the packaging and assembly industry to help going from PICs to the final products. So what we offer are mainly the combination of 3 building blocks. V-grooves or even more 1D or 2D hole arrays for a very precise fiber positioning with guides for beam routing, process converters, couplers, miniaturized and micro-optics, means micro lenses or micro mirrors, as Peter was saying. And our value proposition is really helping customers going from the engineering phase, proof of concept, feasibility, prototyping, where we can offer very rapid prototyping services. Rapid means turnaround times of a few weeks, and we can really help customers to speed up their optimization loops. And then we can go hand by hand with the customer into pilot production and upscale into volume production. And the offer that we have is really monolithically integrated glass components that offer high precision fiber alignment, beam routing, and beam shaping. All these functionalities can be combined with a precision of plus minus 1 micron in a monolithic component. This offers more functionality to the customer, the same price of the component, but also helps the customer to reduce costs for assembly and packaging. With that, I'm done. I'm ready for questions.
Fantastic. Thank you, Rolando. So we have a packed agenda today, so we're going to move on, but we may come back to you if there's a relevant question. So it gives me great pleasure to introduce the second keynote speaker, Nick Saylor, who's the Principal Engineer and Technology Development Manager at Intel. Nick is responsible for next generation photonic packaging technology, development and pathfinding in optical I/O and co-packaged optics applications within Intel Foundry. Nick, thank you so much for joining. If you could share your slides.
Okay, great. Well, thank you very much for the invitation to talk today. So I want to talk through some of the challenges and the way we're addressing those challenges for the scaling of PIC packaging, but specifically from a CPO standpoint specifically. A lot of this will chime with what Peter has just talked about in his presentation. First of all, I'm going to start off by talking through some of the high-level industry developments in advanced packaging, just to set the scene of where Photonics has to adapt to fit in this ecosystem. Advanced packaging is now really key, underpins many of the developments that are supporting the scaling of XPU performance. So we're really now firmly in the era of large, complex multi-chip packages, which are many reticles in size, with lots of different kinds of specialist die assembled using more and more complex assembly flows. And with that, the electrical bump pitches are driving lower and lower as bandwidth requirements are going upwards. And that's putting entire constraints on die placement accuracy from the smaller and smaller bump sizes. So following that, bonding technology is rapidly advancing. So, for example, hybrid bonding is now moving into high volume production. So there are tools available on the market that can achieve very high levels of placement accuracy from die to wafer, like deep sub-micron. In addition to that, we're seeing a long-term trend to transition the core substrate material from organic to glass core substrates, has been mentioned before. And this really is aimed at providing enhanced performance and better thermomechanical stability in the longer term. So overall, we're seeing this progression of die processes to high placement accuracies, and this has direct implications for CPO photonics, really allowing high accuracy, high throughput placement, the kind of tolerances required for low loss single mode coupling. What does this mean from a packaging requirements perspective? Well, first of all, photonics needs to fit into this HVM assembly and test flows, these established assembly flows. So this means that we need to make sure we've got compatibility with the whole chiplet ecosystem. So from a PIC perspective, I mean, for example, adopting common electrical interfaces such as UCIe, making sure we've got compatibility with wafer-level assembly, wafer-level test, and making sure we adopt assembly processes that are compatible with those used for the rest of the package, including the electronic dies. And then the photonic components themselves need to be able to withstand those assembly environments, including reflow, and in some cases, thermocompression bonding. So this can place quite a wide range of different thermal profile requirements onto the components. Now moving to the optical connectivity side of things. So we need to support high channel counts and high bandwidth density. So both spatial and spectral is important here. And crucially, we need very high yielding and known good assemblies in order to support these very, very complex package architectures. Homing in on that optical connectivity aspect. So in addition to the high bandwidth density, the role of the package yield is actually really critical and an important consideration here. So conventional fiber attach processes are typically carried out right at the end of the assembly flow, so as the final step in the assembly. And that means that any yield failures at that point could be potentially very costly, causing the entire package to be lost. And then crucially, this is compounded by the number of optical attaches per package. So for example, in a CPO package that maybe has 8 PICs on it, that final yield is then proportional to the 8th power of the individual fiber attach yield. So in contrast, by introducing the detachability point, the connector at the package edge, this really allows both the optical interface and the connector to be tested individually, and then committed to the package in good state. So that really breaks that dependency on the fiber attach yield and allows for scalability. So here we have some examples of the kinds of things we've been working on to address these challenges and facilitate scaling. So first of all, what I'm showing here is a glass bridge and connector technology for PIC packaging. So we have a glass bridge that attaches to the PIC, contains 3-dimensional waveguides allowing for high density I/O with detachability through mechanical connector alignment features. And then we have a glass ferrule that's integrated into the connector, which has corresponding mechanical alignment features. And this provides a fully CTE matched optical interface all the way from the fiber to the PIC. It supports both edge and out plane coupling, and you can see some examples here of some actual parts. The lower left-hand image there shows a bridge that contains passive alignment features. In this case, these are cylindrical protrusions, which are designed to mate directly into an existing PIC that has V-grooves in it. And then in the middle there, you can see an example of a reconstituted wafer that's used for wafer-level assembly and test on a carrier wafer. And then on the lower right-hand side, you can see a fully packaged example which has the bridge and the connector all integrated in all the relevant mating mechanics to make that work. Okay, and here's another example of some components we've been working on. In this case, these are wafer-level assembly compatible micro-optics. In this example, curved micromirrors. So this allows the conversion of an edge-coupled PIC into a broadband vertical expanded beam architecture supporting both polarizations. So this really helps to facilitate easy wafer-level test and wafer-level packaging. And in this particular example, can also be aligned mechanically through passive alignment, through mechanical features, but also can be faced with using high accuracy die bonding as well. So you can see some of the examples on this page, and lower right-hand side, you can see an assembly as well. So overall, the glass technology and example components shown over the past couple of slides gives us a very wide level of flexibility to work with a whole range of different kind of coupling structures and configurations and really allow for scalable assembly within CPO. Okay, well, thank you very much for the time. Hopefully that gives you some insight and examples on what we're working on to address the challenges, and we'll be sharing more over the coming months. Thanks.
Excellent.
Thank you very much.
Jose, you go.
All right. Thank you very much for a great presentation. It is always fantastic to hear the point of view of Intel Foundry. And we also understand that there are many companies who want to talk to you and discuss with you. Could you share with us, just maybe out of the blue, one challenge that you think the photonics community could help you with?
Yeah, I would say, obviously, we need the whole ecosystem to move forward and gain economies of scale for CPOs ramping. But I think one specific example, Jose, that I think needs a lot of focused work on is the driving down the costs of polarization maintaining fiber arrays. Okay? This needs to become very highly automated and low cost. And some folks are working on this problem, but I'd really like to encourage more people to push this forwards.
When it comes to the fiber arrays, could you give us some specs in terms of what would be the distance between the fibers and perhaps the accuracy between with which you can position?
Yeah, so the accuracy and the position accuracy tends to be pretty good from fiber arrays. It's more the cost, I would say, from polarization maintaining fiber arrays. The fact that they have to be individually rotationally aligned to have the stretch rods aligned to the axis. That's what is driving EM fiber arrays to be substantially more expensive than standard single mode fiber arrays. So that's really the key problem I'd like the industry to push forward in addressing.
Nick, we're going to come back to that, but I'm pretty sure that after this email, there will be quite many companies who want to get in touch with you about this because they are actually heavily working on this. I can see very beautiful smiles from people from SmartAct, for many others. They will reach out to you. I would like to also bring to the floor to discussion some other companies who have been and want to get in touch with Unique and with the others. One of them is one of our sponsors today, one of the market leaders on equipment for passive alignment and wire bonding. I'm referring to the company FineTech. Travis Scott, thank you very much for being with us today. Tell us what you bring to the table.
Can I ask a question to Nick before you move on?
Enrique from Corning, thank you very much
Yes.
and welcome to the meeting. This is not a standard way for us to intervene, but please go ahead and ask your question.
Is this connectors compatible with 3M EVO connectors? The coupling?
No, this is a proprietary Intel connector.
Oh, okay.
All right, thank you very much, and thank you, Enrique, for being with us today. Travis Scott from FineTech, the floor is yours.
So FineTech offers a wide range of manual to fully automated SMD, submicron die bonding and SMD rework systems, as well as the customized process development that supports that at the customer site. We offer a wide range of technologies and modules to address various different types of die attach and die bonding, everything from eutactic adhesives, thermal compression, hybrid bonding. So all these technologies that address PIC to interpose the optical side, the electrical side, and the co-package side. Our systems offer for a very flexible and versatile change from different processes and R&D inside of the same system, as well as moving on to fully automated production systems. We do offer the submicron high accuracy alignment and placement required for PIC assembly. Sorry. Just like everybody in Europe, I've been sick the past week, so I'm just struggling a little bit. So we also offer the high accuracy placements required for the PIC assembly in these kinds of packages. So we're at FineTech for die packaging, die bonding, and SMD rework. If anybody has questions, feel free to reach out, or we can hang around and answer some questions later on. Thank you.
Thank you very much, Travis. From FineTech, let's go to FiconTEC, and they are now enabling a fully automated production line. They are the masters of active alignment. Anton Bano, thank you very much for being with us today. Please share your slide and tell us what we can do for you and you can do for us.
So as you introduced us, FiconTEC has been supporting the photonics industry with automated solutions for assembly and testing since almost 25 years now. And we have proven to be and we're well known to be a very reliable partner for high volume manufacturing, supporting the biggest players in the industry with an installed base of hundreds of machines in the Southeast Asia and not only, and a huge and skillful service team there just for this installed base machine. However, what I want to highlight here today is that even though we all want to talk about volumes, and that's why we're gathered here today actually, and that's where the biggest challenges lie ahead, still for many, the road to high volumes can be quite long and bumpy. And photonics is a very dynamic industry where new ideas are being applied every day. And these ideas usually come into the game from university R&D labs, spin-offs, startups, etc. So we are here to support you to start your journey, thinking about automation from day one by offering entry-level, user-friendly, flexible and modular solutions with great support and ad hoc trainings, digital twins, etc., such that you can get familiar with industry-level automation from the very early days. So our reminder for this meeting is that we're here to be your companion during this long road to high volumes. Thus, our illustrated portfolio in the slides include lab systems with production capabilities, production systems with development capabilities, and then the third option is automated production system with automated loading and unloading. And you can think of all these three cells not only for assembly but also for testing, both in die level and wafer level testing. And the very end could be thought about automated loading and unloading of wafers in a wafer level tester. And FiconTEC is working hard on this as well and is offering very standard solutions nowadays. The very high-end solutions that lies here on the top right side of the slide, we talk about fully automated production lines where the operator can really load raw material in and get fully automated, assembled and tested parts out. So that's just one slide showing what FiconTEC can do for you. And what you could do for FiconTEC, I think there are quite some nice examples here in the panel as well. We have quite some nice collaborations with instrumentation companies. Like in this case, we have Quantifi Photonics here. We have with laser manufacturers like Femtum around. So we're looking for continuous collaboration in the photonics industry to drive the photonics assembly and testing forward and to tackle the new high volume challenges that we're facing every day, to tackle them together.
Thank you very much. And we actually have a question for you. The question is coming from Stuart from Guchan House. Go Stuart, go ahead and you unmute and ask the question yourself.
Hi. So as you say, Anton, it's important to have a smooth and well optimized scale up process. I'm just thinking about, for example, if an organization was to take one of your lab systems that, for prototyping, for early stage development, and then optimize an alignment and assembly procedure during those earlier prototyping stages. Could the processes from that just be directly copied over to the larger scale systems? Is the hardware or firmware, I suppose, and software on your tools directly cross-compatible, or is it would it need redevelopment, translation across?
Thanks a lot for the question. So that's a very good question, and that brings me to another topic, which because of time I couldn't mention here, but thanks for the question. So all the FiconTEC machines that have been installed so far in the market, and that's around 1,500 machines, from single cell machines to the very high volume manufacturing sales of a production line, they all run in a program that is homemade by FiconTEC called PCM. So that makes it easy both for the user to transfer his own knowledge into adapting to the new high volume manufacturing cells, but also for FiconTEC to transfer the
allow
projects.
me to interrupt you here, because one of your customers could actually provide the answer, and I prefer if it happened like this. Simon Kiven, the CTO of Photonics Foundry.
Sure.
Simon, you are a customer of FiconTEC. Tell us your experience of transferring one process to another in a FiconTEC system.
Hey everybody, thanks for the introduction. In general, this can be done. So transferring processes between FiconTEC system definitely is possible, although some adaptations from one system to the other have to be made, maybe some position renaming or things like these, but in general, these processes can be transferred.
And Simon, that's something that Photonics Foundry can actually assist. So thank you very much for being with us. Andon,
for sure.
Travis, stay with me because we want to come back to you after the presentation by Fix, but allow me to bring somebody else to the table. One of the key companies at Optica is Quantifi Photonics, because they have been working with many of our equipment manufacturers and they provide test equipment. Please stop by their booth at OFC. Kees Popstra, thank you very much for being with us today. The floor and the attention is yours. Show us your slide.
All righty. Good morning, good afternoon. John and Jose, thank you very much for organizing this webinar. I think 2025 is going to be a very interesting year for our industry, because what I'm seeing, and I'm sure that a lot of folks in this meeting are seeing the same, is that people are really planning to go to the next level, really scaling to high volumes for photonic IC technology. And of course, we play a key role in that. So we really focus on photonic IC ATE testing, as well as the parallel high-speed I/O test, which is really wafer-level testing, as well as the package product level testing. So let me go to my slides. Let's see, can you guys see my slide? Yeah, I think so.
Yes.
So obviously we know what's happening in the industry, so I don't want to elaborate too much on it, but really there's a couple of key elements that are really driving the requirement. So it's the increased beats from density, multiple channels, multiple wavelengths, or a combination of that. It's like these new optical interconnects are based on photonic IC technologies, so wafer-based technologies, and they have really ultra high speed interfaces. It starts at 32 gig all the way up to 200 G per channel per wavelength. So, key technologies are Terafy, IO Labs, we have Passage from Light Matter, we have OCI from Intel, just to name a few examples. So what are the solutions that we need to be able to scale these technologies? So one, of course, we need to do wafer level testing, and we also need to look at the package level testing. So let's talk a little bit about that. So photonic IC ATE test is kind of the equivalent of the traditional semiconductor ecosystem. You need to really replicate that to be able to do that. So the idea is really, you have a box of wafers, you feed it into kind of a machine like an Advantest, a FiconTEC, or a Teradyne machine, and then you get a fully qualified wafer. Out of there, you know exactly which wafers are meeting the specification, or which devices on the wafer are meeting that specification. Of course, it's very critical that you do that fast and cost effectively so that you know which parts, which dies to use to go to the next level. And what we've seen is that you really need to make sure that you do very rigorous DVT, and based on that, come up with a limited test set that is sufficient to qualify wafers at the wafer level test. And really what it means is our experience that you need some kind of lasers, polarization controllers, power meters, and optical spectrum analyzers, and some equipment like attenuators and switches to enable that. And our solution is based around the industry standard PXI, so it has high density, is very flexible, and you can combine it with other elements such as SMUs. So that's the first stage, really industrialized wafer level testing, very, very fast and cost effective. So that's, for the wafer. And then, of course, you want to go to the next steps into your manufacturing cycle. You get your singular die, multi-die combinations, or optical sub-assemblies, and the package level product. So packaging obviously is a very critical step in the manufacturing chain. It's really the last step before you ship the product to your end user and before you deploy it in the system. And you really need to make sure that it is meeting all the requirements. And obviously, packaging has a very significant impact on the product. You go from kind of an optical subassembly, you put like a package around it, wire bonding, and so on. So it really changes the physics. So there is a hard need to do at-speed validation of the packaged product to make sure it meets all the requirements. So in order to do that cost effectively, you need to really focus on parallel testing. So we have a solution, we developed a solution for that. It's the QCA series in combination with the Vis-I jitter and eye analysis software. So it's a fully parallel test solution, so you can do a really cost-effective screening of your packaged device to be able, again, to scale your manufacturing to high volume. So that's what we do in a nutshell, test solutions for wafer level testing, photonic IC ATE test, as well as packaged product testing with our parallel high-speed I/O test solution. So that's Quantifi Photonics in a nutshell.
Thank you very much. And we love Quantifi Photonics all the way from beautiful New Zealand. You always have great booths at OFC. We can't wait to visit yours. There's a question for you in the chat, and it's coming all the way from Celia Milon from Raven. Celia, would you like to try to ask yourself?
Yeah, I was just curious when you mentioned that you need lasers for testing. What type of testing, what are you testing actually, and what type of laser are used?
It's a great question. So, the key is really that in R&D and DVT, you need to do a wide variety of testing to make sure that you understand your technology. Obviously, that is not usable in wafer level testing, at scale wafer level testing, because you need to really have a limited test series. So typically, what people do is they do just like insertion loss, return loss, maybe a little bit of wavelength dependent and polarization dependent loss measurement. So depending on those requirements, either a fixed laser or it's a tunable laser that you can use for this kind of parametric optical testing. But it depends a little bit on your device, but typically it's, of course, like we focus on 1310 O-band applications.
What a way of starting the meeting. What I would like to let everyone know is that the meeting is really going on in the chat. So please contact each other if you're not doing so already. We started with Intel. We had the Tyndall pilot line. We also heard about Europe PICs. And now we're going to hear about what we love the most in Optica. Optica is a collaboration platform between companies, and when two companies find a good reason to work together and they make something bigger than they could have done by doing it themselves, it is our time to tell them well done and to give them the visibility that they deserve. I'd like to introduce a combined presentation between a company enabling the miniaturization of photonic systems by embedding planar optical waveguides of photonic systems with another one that has been doing packaging, service, and testing all the way from the Netherlands. I'm talking about from Switzerland, Vario Optics, and from the Netherlands, Chip Integration Technology Center, much better known as CITC. Sander Dorrestein and Nicolai Flory, the floor and the attention of everyone is yours.
Hi, good afternoon. Thank you very much for the introduction. I'm sorry to tell you that Nicolas Fleury is not present, but that I will take over his presentation.
But Valentin, he
I'm
looks
not
so good in my
interested.
video in the opening. I cannot believe this happened. I'm kidding, of course. Thank you so much for
Don't
being here,
worry,
Valentin.
don't worry, it's fine. Yeah, just let me introduce you quickly. So I'm gonna talk about PIC packaging, a way towards semiconductorization. Varioptics is a SME-based company that is based in Switzerland, and we've been around for over 15 years and doing planar optical waveguides with a large portfolio from multi-mode waveguides in the area of 500 micrometers down to below 3 micrometer waveguides in silicon single-mode applications. We always try to be very close with optical and electrical interconnects because we think that is the way to go in the future. Now, focusing on single mode technology, things we're talking about PIC packaging. So what we offer is two kinds of coupling schemes, because coupling, I think, like the packaging is one big like obstacle in the high volume manufacturing of photonic devices. So what we offer is planar waveguides that have a very high confinement and allow therefore a very high channel density with pitches down to below 10 microns. So the large number of IOs is only limited by the PIC and not by our waveguides. We also do a mode field matching and reducing coupling losses, for example, to the fibers. And also we can do a fan out to match standard fiber arrays. Now, usually with edge meeting devices, like alignment is very critical and often used active alignment. We think passive alignment, or at least a semi-passive alignment, is the way for high volume productions. And we demonstrated that with using micromechanical devices and optical, or actually visual-based pick and place tools with alignment precision better than +- 1 micrometer. So, and we get with these, we get insertion losses from chip to interposer of less than a dB. And also, of course, we have some losses on the glass fiber side. But still, if we go from glass fiber to indium phosphide or something else, that will still have higher losses there. The other option to do a coupling is the evanescent field coupling, where we use PICs and polymer waveguides with open cores, bring them in very close contact, and having tapered silicon waveguides or any other, they will force the energy out of the core of the waveguide into the evanescent field and thus couple into the waveguides. Now, with this, we get much easier coupling because we don't need the very precise set alignment that we use in buck coupling. And also the alignment tolerances in X and Y are more relaxed than with the buck coupling. Also, compared to like grading couplers, the waveguides, so this coupling is not dependent on the wavelength, so independent of any variations there. And also with these evanescent field coupling, there is a possibility of wafer-level testing, which is in the buck coupling not so easy. We would have to do die-level testing. And so we believe that the way to semiconductorization, so meaning a high-level production using the tools that are there from semiconductor industry, from PCB industry, like flip chip bonding, die bonding, we think that is the way to go also in photonics. And in the collaboration with CITC, we do have a project where we develop an assembly processes and concepts for multi-chip modules, so where we put several PICs together on one board, where we can use any type of PIC, and so meaning silicon nitride or silicon photonics or indium phosphide, it doesn't really matter.
and also using completely passive alignment schemes. And we believe also that we could show already in simulations and also first tests that we could go coupling losses from PIC to the polymer far below 1 dB, and thus reducing overall losses. Also, we are always focused on not only do an optical package, but having the electrical side very close by. And furthermore into detail, I think Sander from CITC will go. Please, the stage is yours.
Yeah, thank you. Thank you for the nice introduction. So let me share my slides. So first, I'm Sander Doornstein from the Chip Integration Technology Center. So we are a non-profit research organization, and we focus on advanced packaging for both semiconductor and integrated photonic devices. With that in mind, so with our semiconductor background in mind, we are currently working on what we call semiconductorization of the integrated photonics. And so we would like to make use of known semiconductor technologies and tailor them towards integrated photonic products. And so we have a packaging concept in mind, which is based on panel scale assembly, where we rely on pure passive optical alignment. And so we think that is a much faster process than active alignment, whereby the use of polymer waveguide structures, we achieve a very low optical loss interface. But beyond photonics, it also needs an electronic integration. And so we are developing additive manufacturing technologies where we create electrical RDL on one side of the panel, where we also achieve very high bandwidth electrical interconnects. And so we target beyond 140 gigahertz as data rate. And of course, as also mentioned in the previous presentations, this package concept should feature a pluggable optical interconnect. So in the core of our package concept is that we start with a glass panel, and on one side of the glass panel we create an electrical redistribution layer by additive manufacturing, and this allows us to integrate the electronics on one side of the package. And then by high aspect ratio vertical interconnect, we create the electrical part to the photonics, and on the photonics side we use the polymer waveguide technology on vario optics to make an optical redistribution layer on the opposite side of that panel. Our mission there is to bring these technologies to a certain technology readiness level so that it can be adapted by the industry. This is showing our first results of the electrical interconnect. Just some highlights here. So by this additive manufacturing process, we achieve a resolution of 15 micron. And so 15 micron line width with 15 micron spacing. Bear in mind that this is a pure additive process. So we do not do any etching. We do not wash any material away. So we only print what we need. And so it's a much more sustainable technology. And by this technology, we are capable of making high aspect ratio vertical interconnects. And with certain designs, we can go beyond 140 gigahertz. And so we can really boost up the data rate from such kind of packages. But we also are working towards this optical interconnect. So here we rely on the evanescent field coupling, and we have optimized the design from PIC to the polymer waveguide structure, where we have a significantly less than 0.2 dB loss at the interface, still having a relaxed alignment tolerance of 2 microns. And this is then where we partner with Vario Optics. So they provide us with the technology. We make our own photonic test die to actually demonstrate this the technology building block. And so this is one of our first assemblies where you see the polymer waveguides merged together with the photonic circuit. And we are currently evaluating the performance of this assembly. Thank you.
Great, thank you, Sander and Valentin. I was really excited to bring this collaboration to the meeting. Very much looking forward to following the project and how the next demonstrators perform. So I'd like to bring to the meeting now another meeting sponsor, New Photonics, who are enabling higher reliability volume manufacture of PIC products for transceiver modules through improved system design and novel integration of lasers. Doran Tal, please share your slide, and the floor and the attention of everyone is yours. Thank you.
Awesome. Great. Good morning. Good afternoon, everybody. It's great to be here to discuss this scalability and PIC and manufacturing and test. I think this is one of the industry's most critical challenges, and it's great that Optica is putting this forum together. I'm learning a lot, and I see a lot of good partners here. So New Photonics is focused on high performance integrated photonic solutions for next generation optical interconnects. We are a fabless semiconductor company. We're a designer, developer, manufacturer of photonic integrated circuits for pluggable optical modules in hyperscaler data centers. So our solutions include a highly integrated 1.6 terabit per second PIC for DSP-based and LPO-based optical modules. Our solutions include integrated lasers, modulators, and our optical signal processor. So to fulfill the rapidly rising data center optical interconnect demand in high performance compute and AI, I want to share with you what we're doing to innovate and unlock manufacturability, excuse me, scaling bottlenecks with our laser integration techniques. So really at the core of our product is a novel approach to heterogeneously integrating lasers at the wafer level. What this really means is that there's a direct integration of 3-5 onto silicon photonic wafers. This eliminates the need for discrete or external lasers attached and the complex alignment steps that are associated with that. And this approach really improves the coupling efficiency by over 90%. Obviously, it reduces the OEM manufacturing costs. It accelerates production timelines and enhances reliability, making it a scalable and a cost-effective solution for high volume PIC deployment in data centers. So with the traditional approach, where external discrete laser sources are placed like EMLs or PICs with external DFBs or other lasers, this requires additional assembly steps, including optical die attach, alignment, wire bonding, and such. That method really increases manufacturing complexity and CapEx and labor costs associated with slowing scalability. So from a fabrication perspective, our integration approach really shifts the laser functionality from being the last manual system level production stage to more of a CMOS chip-like manufacturing step. And by reducing the need for added components, we really eliminate points of failure and degradation caused by issues in optical coupling and optical loss. So since the active alignment and accuracy requirements from external lasers place really a substantial burden on manufacturability and scaling, the move to the integrated laser really represents a significant improvement in terms of fabrication, efficiency of the production scale, and the performance. So if you have any questions or any more interest in our silicon photonic integrated laser solutions, please feel free to contact me. Check out our online blog about laser integration and look for a deep dive in next month PIC magazine.
Great. Thank you so much, Doran, for the slides and for the sponsorship of the meeting. I'd like to now move on to another collaboration that we've brought to the meeting. It's another Netherlands-based combined presentation between meeting sponsor Jeroen Dries at Fix and Douw Geuzenbroek at Brilliance on how Brilliance are combining their expertise with Fix's one-stop shop from design to volume production to produce the smallest and most efficient PIC-based RGB laser chip. Jeroen and Douw, the floor and the attention of everyone is yours.
I'm not sure if everybody knows already Fix, since we have been around already for like nearly 8 years now. But we are a packaging and manufacturing company located in the Netherlands, doing all kinds of photonics packaging and assembly. And as of last year, we moved our own facility and really scaling up as contract manufacturer within Europe, doing fiber attaches, hybrid integration, and DC and RF interfacing. And to give some product examples, it's like stuff being done on a printed circuit board, small components, larger components, as Tyndall was showing as well. So we also do wafer level assemblies, prototyping that out for various markets, traditional packaging and butterfly style interfaces, but also the more uncommon form factors that need to be scaled up for different applications. And today I'm going to talk a little bit about the need for the hybrid integration that we are working towards as well as the heterogeneous integration that we're doing. So when you're looking to the current state of the art that we are manufacturing, we do a lot of hybrid integration using edge coupling with different material systems and connecting them to each other, as you can see on the bottom left image. And the main reason is that we need to integrate all kinds of different material systems on the most effective way. And most effective for prototyping on the edge, what we're seeing is you have a lot of flexibility. Also, if you have wafer runs that are failing for the prototyping, you're much more flexible in getting drop-in replacements and to develop your prototype from there. But when we're looking further and further down the line for scaling, it's like the edge coupling is limited as well when it comes to functionality and the amount of volume and cost reductions that you're capable of achieving. So for flip chipping, and that's another way of doing this hybrid integration, we're looking as well, what can we do there in terms of scale up? So the setup cost is going to be much higher since there's more process development up front. You need to maybe do dedicated wafer runs, but in the end, when you're looking to very high volume, the cost is taking out. Monolithic integration, we see as well, like it's very intriguing to see and appealing to go in that route. So multiple research groups are working towards it. But what we're seeing is there's so much different flavors and reasons to integrate materials, whether it's BTO or lithium niobate or from the visible wavelengths, what we are doing for Brilliance, but also infrared or even mid-infrared. All these different material systems are not compatible and directly integratable onto one platform. So what we're seeing is the flip chip integration, and FineTech has been providing a presentation as well. We have some FineTech tools installed, and they're capable of doing this flip chip integration inside a cavity, aligning to waveguide. So what you're seeing here is a 3-5 die aligned with a waveguide, and it could be any kind of chip platform. It's not limited to silicon, so it's really depending on like the interfacing and functionality. The main criticality is about the vertical stops that you need to be able to implement in your platform, either on the silicon side or on the carrier side, as well as on the flip chip side that you're putting down. So for us, what's really critical and what we need to control is the solder composition, since that's going to give you the mechanical stability. So for example, the shear value, so how strong it will stay there. Also for electro migration, so is it going to be reliable over a large amount of time in combination with humidity and high temperature. Thermal management, so how do you make sure that the heat goes out on a certain direction? And of course, the solder part design. So when you're looking to the alignment and the optical power output, how can you make sure that when we put a die there, that it remains there? And what we are seeing is that this is traditionally driven by the datacom market, but we see other markets now widely evolving. And an example for that is AR, VR, but also biomedical light source integration in combination with nitride. And it's really overcoming the cost of polarization maintaining fiber integration. And we heard it before as well today, from Nick, PM fiber attaches and PM fiber array manufacturing, that is going to remain costly. And by doing this kind of integration, we can take out the fiber interfacing. In this case, we have been buying a AMICRA tool. So we have been working with FineTech on a component level, so die-to-die level. But for the volume scale up, we have been choosing for the AMICRA because of the faster speed that the machine is having and the more advanced wafer level processing that it could do. And I think that's also giving the strength directly of the whole ecosystem, since we need to have machinery and equipment in all kind of phases of the development journey that we're doing. So in this case, we have an 8-inch wafer substrate handler, so we can do the 8-inch wafer handling, and also we can do the 12-inch if required. We can put it in there. But we see that the majority of the integrated photonics right now is on the 8-inch wafers. What we also see and what we get to learn in this whole development cycle is like, yes, we want to do a process development, but also we need to do in situ testing and characterization. So I think that's again also where it's very important. How are we going to do the wafer level characterization? How do we do the die shear testing? And how are we in the end going to build a complete production line of it? So for now, we have been setting up a small prototyping line where we can do this whole circle in-house and validate like, well, what are the process parameters? Can we optimize it to allow for an optimal coupling efficiency from the light source into the waveguides? And then for phase 2, we're scaling towards production with in-situation testing and validation. And I think this is a nice moment to hand it over to Douwe so he can showcase how we have been doing that for them.
Yeah, so my name is Douwe Geusbroek. I'm CTO of Brilliance. And Brilliance is in a way different field than most of you are, where most of the photonic integrated circuit has been. We are in AR fields, in the augmented reality. That's a field that is emerging, and so I bring you in this short presentation. I will show you what PICs can bring in this field. I think most of the technical part you have heard from Jeroen, what we are working on, but why are we doing this? Because we are targeting, basically that everybody will throw away their smartphones, where they will put it in the bin. Sounds crazy now, right? But nobody is using a BlackBerry anymore. You also threw that in the bin. So the classes are a new interface to computing anyway, and a new interface to the information that we take onto us. And there are many issues still there to get that actually done. Part of it is that the projectors are still too big and too bulky and too power hungry, and that's where we can help. Because the technology that we bring in, we are bringing one of the first. We bring in a photonic integrated circuit technology into this field, which has a way lower power consumption, is much smaller, has much higher peak brightness, so you can also use it outside. And what most of our customers like, we bring a technology that can actually scale, and that is what resonates very well with many of the people that we work with. It is a wafer scale technology that we use. So one of the challenges here is that we work in the visible light, right? And visible light is typically made out of 3 lasers with red, green, and blue lasers. You want to have lasers because it's a high brightness, very right. The photons that come from a lasers are you have many photons that you can actually use. So you like that. That's efficient. But the 3 lasers need to be combined, all on a spot that is as perfect as possible, because you want to scan it, or you want to use it as a backlight, or you want to do a holographic means with it. It can be done. It is being done with all kind of micro optics, but that is a still relatively large component with many different components to be placed and aligned precisely. That can be done all on chip. So we are using a silicon nitride chip there, where we flip chip bare visible laser diodes onto, and that's the product that we are working on. It looks like this. It's only 4 by 4.5 millimeters, where you have red, green, and blue laser diode flip chipped passively. Right, our target is to do it all passively because of the big volumes that we are targeting and the cost that is related to that. And together with FiCS, we are doing the process optimization there with all the tools. I think there the ecosystem is always a good word there, right? It's an endeavor that we take which can be done now. 10 years ago, this could not be done, right? It's all sub-micron alignment. It's all visible light, so we don't want to have any epoxies close by. It is a challenge, but it can be done. And we are showing this product now, and we are launching this product. We are quite ambitious in the scaling part there, right? If you read all the third-party market reports, nobody is doubting that it will come, right? The question is when exactly, right? And maybe we first end up in a heads-up automotive, or we see closer by industrial applications as well. But the goal on the end is the AR glasses in the big volumes, and you will see more and more integration into a wafer scale version of this coming. So that is basically also what I want to show here, right? It's a component that we make. The closest by is a combination with a MEMS mirror that you call laser beam scanning. So a MEMS wafer scale combined with a laser-based wafer scale component, and also there all the photonic integrated functionalities that we know from the data and telecommunication world can also be of use in this world. So as a conclusion, right? Photonic integrated circuits for visible light open new markets, and I think wafer scale photonic integrated circuit assembly is the only route to reach there, and you will all be wearing glasses. Thank you.
Great, thank you, Dev. A very exciting project, and I look forward to seeing you reach those milestones. A quick question from Saud Nazir from Nokia. Do you want to?
Hi, John. I had a question regarding free space optical assembly. If FiCS had that expertise of providing millimeter scale optical assembly, for example, in the case of a gold box package that's fiber pigtailed with optics assembled inside.
Thanks very much for the question. So the short answer is yes, we have it, since we see more and more that people are looking to get isolators integrated in between multiple PICs. So I think the most complex module we are doing today is having more than 5 PICs into a single box, all connected with free space lenses and with isolator components in between.
Great, thank you very much.
So another collaboration FiCS have been working on recently is they've been showcasing another partnership with RJR Technologies, who are offering liquid crystal polymer air cavity packages for integrated photonics. So we have multiple people from RJR here. So Marco Kilnick is here. I believe he's struggling with his voice. So we also have Will Salhuana here, who's going to speak to the slides. So thank you. Please share your slides and tell us why this packaging solution is particularly suitable for volume production.
Yeah, okay, great. Thank you so much. And again, good to see both you and Jose virtually, as well as Jeroen and Sander. We're here to offer an LCP-based package. A lot of talk about semiconductorization of photonics. I think we can definitely help do that. So we're going to introduce our packages. RJR is a privately held technology and manufacturing company. We've got 3 locations. The first one is in Phoenix, Arizona, where we have our headquarters and our main manufacturing facility. Our second is Hayward, California, where we do R&D and manufacturing. And then the Philippines, where we also have engineering and manufacturing. We also have a presence in Europe, where we have Marco, who unfortunately is sick today, but he is commanding the slides, and Sven Knipscher out of Germany. So we have a presence there for people to contact us directly in Europe. We deliver cutting-edge packaging solutions through the use of liquid crystal polymer, our proprietary B-stage epoxies, and what we mean by that is we actually formulate the epoxies used in our packages, and we use precision injection molding. Down we have 3 distinct offerings. One is the B-stage epoxy component, so we actually apply the epoxy into the component of it can be supplied by the customer or it can be procured or built by us. What we mean by B-staging is we advance the epoxy to where it goes into a semi-solid state. It can still be further advanced when heated to basically make the hermetic seal or the near hermetic seal. The second portion of our offering is an air cavity plastic package, where it all comes together, where the epoxies, LCP, the injection molding. And what we've done there is we provided best-in-class performance and time to market. And accompanying that so that we can really help on the assembly side, we offer the sealing equipment to basically attach the different package components using our epoxies and provide you about a 99+% yield on these. Now, we've done what is desired in the photonics industry in terms of bringing the IC chain into this. And so years ago in the base stations, ceramic was the package of choice. It was hermetic, and we saw an opportunity. We came in first with our B-stage epoxies and then with our air cavity plastic packages, and we provided to the customers a higher performance device. We basically improved thermals by 20%. We have a extremely high reliability. As you can imagine, in the base stations, the mean time between failure is 20 years. We provided 80 million ACP packages to that market with 0 failures reported to date. We also provided short cycle times and low NRE. We basically brought it from months to weeks. And on the lower costs, we brought a 50% cost reduction from using the traditional ceramic to going into our plastic solution. So we're trying to do the same in the photonics. We've partnered with FiCS and CITC, two previous presenters, Jeroen and Sander, and we have now defined and brought to market 2 of the butterfly type packages. The first one is the 14-pin, which is shown on the top, and the second one is a 40-pin PIC module. And this basically provides flexible substrate and lead frame design. We have the lowest cost per unit and lower assembly. We can basically assemble this in strip, so you don't have to do individual assembly because you can use the strip that is used for the injection molding on the assembly. When we say flexible substrate and lead frame design, we can basically change because the package is brought together with the epoxy. We can use many types of thermal bases. That's a choice of the customer. We can obviously insert PCB type materials in here. And if you use the outline of the package, you can basically do a turn by just changing the lead frame and have different types of lead configurations in your design. As again, we've proven the reliability in high volume applications in the RF world, and we've got this 14 and 40 pin packages. One of the previous presenters showed a PCB, BGA type. We've done that. We've done QFNs, we've done BGAs. So bringing that capability to this market is something we have the expertise to do. Next slide. So for further context, as I mentioned earlier, we have 2 individuals. One is in Germany, Sven, and Marco, who's in the Netherlands. Thank you.
Thank you so much, Will, and Marco on the back end. There's been a couple of questions in the chat that Simon Kibben from Photonics Foundry has kindly answered. It was about the transparency windows of your epoxies. Would you corroborate the answer that they can be used from 700 nanometers and above? Because shorter wavelengths will degrade the epoxy, or?
Yes.
We don't see any reason why it can't. Obviously, it needs to be proven, and that's where we're offering the technology. Like I said earlier, we're partnering with CITC and with FiCS, but certainly we're looking for the end user to demonstrate these capabilities. The actual lid can be an LCP, it can be glass. We've done many devices with glass and using our epoxy. So these are all things that the application would that we need to prove in the application.
Okay, and very quickly,
I don't see any reasons not.
We have a quick question. Ian McKenzie, did you want to quickly ask your question?
Yeah, just a quick question. Hi, it's Ian McKenzie from the European Space Agency. Hi, Jose. Good to see you.
Hi.
Just in terms of this near hermetic, what does that mean in practical terms? I mean, you know, have you got some examples of how this near hermetic sealing works in terms of
basically when we
times?
say near hermetic, of course, hermetic basically says that you have to pass fine leak test, and it's how fast moisture penetrates into the package. We believe we can go to about 10 to the -8 in terms of that. So that's what we call it, a near hermetic. We also define it as a highly reliable device. So this is where, I mean, one of the questions or one of the challenges that the package has, which is the same challenge we had in the RF world, is that if you're trying to go to high volume and low cost, you have to change things. So is a hermetic package really required? If you require a hermetic package, then we're not. But if you want a near, which means for us, it's good enough that it will comply with the new standards as the industry moves to high volume manufacturing, then yes, that's where we live. So that is that's the inflection point that we're looking for. And in terms of the relationships that we built so far, it looks like the industry is certainly looking for that, and we're ready.
Great, thank you so much for Ian for the question from Isa, and thanks Will and Marco in the background for RJR Technologies. So
thank you,
next
thank you again.
I'd like to introduce the final combined presentation between Sumitomo Electric, who will discuss some of the challenges faced from the customer side, and meeting sponsor Vanguard Automation, who will showcase how they're tackling these challenges and using the opportunities to enable industry partners to go to high volume productions. Yasutaka Mizuno and Laura Horan, the floor and the attention of everyone is yours.
And thank you, John and Jose, to hold this excellent event. So my name is Yasutaka Mizuno from Sumitomo Electric Industries. Today, I will talk about 3D printed micro-optics for co-packaged optics. First, let me introduce Sumitomo Electric. We are a manufacturer of both active and passive optical devices. For active device, we fabricate indium phosphide wafer, DFB laser chip, optical sub-assembly like TOSA-LOSA, and tunable laser module. And for passive devices, we fabricate optical fiber and its related products, such as optical cable, connector, and splicers. So next, I will explain about co-packaged optics, CPO. So as you know, data traffic is growing rapidly due to the progress of AI and machine learning. CPO is attracting attention because it can improve transmission speed and reduce power consumption. In CPO, electronic IC, photonic IC, and fibers are integrated in this small package. We should pay attention that 8 or 16 optical channels are accommodated inside this small package. So the density is quite high. Also, if the number of channels get further larger, the size of optical coupling part would be the bottleneck for the beach front density. So to achieve high density chip-to-fiber optical coupling, micro-optics is a promising technology. So one example is facet-attached micro-lens, FAML. The micro-lens is directly attached on the device facet through 3D printing. And 90-degree bend or beam expander could be achieved, like this picture. Another example is photonic wire bond. The two devices are directly connected by the resin waveguide, which is written through 3D printing. In this case, the important thing is that positional misalignment between these two devices could be compensated by the resin waveguide. So today, I will show one use case of micro lens, namely vertically coupled beam expanding lens. The concept is shown here. A free-form lens is directly attached on a PIC and a fiber. The light is horizontally emitted from PIC edge coupler, and it is reflected by the mirror toward vertical direction. The light is reflected again by the mirror on the fiber side, and the light is coupled to the fiber. In this case, the output beam is expanded by the convex-shaped mirror, so the alignment tolerance is enlarged. The right side graph shows measurement results. The alignment tolerance is as large as 10 micrometer. And also the low insertion loss and flat wavelength characteristic is observed over 100 nanometer wavelength range. So this range will be very useful for detachable connection between PIC and fiber. So finally, I will talk about the challenges of micro-optics for mass production. One of the challenges is reliability. For CPO, we should comply two types of reliability specifications. One is for telecommunication. So long-term reliability is required, such as temperature cycling, damp heat, mechanical shock, and vibration. And another requirement is for semiconductors, and the severe condition for packaging is required, such as 260 degrees C reflow. So we have already demonstrated that the 3D printed lens can satisfy these specifications. Another challenge is takt time. So assumes that the total production is 10,000 CPOs per month, and each CPO has 16 channels in one package. In that case, total amount of is 160,000 lens per month. So the takt time per one lens should be as short as 17 seconds. So this is a big hurdle for mass production through 3D printing. So we are working on these two challenges right now. Oh, that's all from my presentation.
Thank you very much. We always love to hear Sumitomo talking because you take the photonics technology to a semiconductor business. One of your partners is Vanguard Automation, and Laura is here with us. Laura, please take it over, and I know you have something very big to announce.
Hi, thank you very much, and thank you, Yasutaku, for outlining the challenges you're facing with going to volume production for co-packaged optics here. Yep, so I want to talk to you today about how Vanguard Automation is trying to solve the challenges of going to higher takt times. And right now we're looking at wafer level and batch processing for photonic integration. So you can see on the right-hand side of the screen a video playing, and this is showing you how our systems and solutions are being used to process wafer level. This can also be elevated to batch processing. What we
Laura,
do
are you saying that you have a wafer level process now for photonic wire bonding?
Yes, you can see here.
Oh, wow.
In the screen you have on the screen, this is actually the other system, the Reprise, doing the pre and post development of our systems, and then also do the encapsulation of the photonic wire bonds. But in the next clip you will see, we'll come back soon, you'll see the Sonata, which is responsible for 3D printing of photonic wire bonds at wafer level. Here's the wafer being put under the lithography objective, going into additive production of photonic wire bonds. And then back to the Reprise system for the pre and post development. So the benefits of going to Vanguard Automation for the solution is, of course, the ability to integrate active devices into hybrid multi-chip assemblies. You have high reliability and low loss, as shown by Yasutaka in his presentation. Damp heat and also the reflow soldering tests are passed for these processes. And you can do mode field matching for low loss optical connections. And also by having a pass-learned process and additive manufacturing, you've got to relax pick and place time. So it's really simplifying the production processes. So
Laura,
thank God
congratulations. This is really big. This is huge. I am very impressed. We finally have a wafer level process for a technology that in many other meetings we've been discussing whether it's suitable for volume production or not. This is fantastic. We have a few questions for you. The first one is coming from Chris from Iponics. How is the dispense of the resin handled for wafer level testing, for wafer level printing? How do you handle the resin? How do you handle
we have an
the
automated
dispense of the
dispenser.
resin?
Yeah. We have an automated dispenser inside the system for point dispensing of resist. You can also use the Europrise system for putting resist onto the entire wafer level.
We have a lot of questions for you, Laura, but I want to go to one of the people who are using the technology of Vanguard Automation. I want to go to Keystone Photonics, Philip Dietrich. You are with us right now. Please share your slide and let us know how, from a wafer level process, congratulations, Laura, this is fantastic, to wafer level testing enabled by the same technology. How can you do it?
Yes, so thank you very much for the kind introduction. So yes, at Keystone Photonics,
Did you see what Laura just presented, Philip?
Yes, of course. Yes, I know. I'm super happy. You know, my
go
heart
ahead,
is jumping.
Philip.
You know, no, this is feels almost like a newborn child. It's just saying. No, I mean Keystone Photonics is also a Vanguard customer. We're using our the technology for a very specific use case. So what you can see here demonstrates the basic technology and what we do. We create optical components like this micro optical wafer-level combination on optical arrays, other components.
You move your microphone down. Keep it close to your mouth.
And that allows us to tackle one of the biggest challenge in photonics manufacturing. That is wafer level testing. There are two flavors of this. One is surface coupling. We can do grating coupling. We can do lens coupling. So we can also test CPO interfaces meanwhile, and we can do edge coupling. And what Keystone has done has moved the technology in this particular use case to state where it is production ready. So we are delivering to all major wafer level testing companies, FineTech, FiconTEC, MPI, and others. We supply to a majority of silicon photonic foundries, and thus have made the step to production readiness. And we're happy to engage with more partners. We're happy to enable the industry to do wafer level testing and to solve that particular challenge.
Thank you very much, Philip. So let's go to one of the market leaders of wafer level testing. I'm really more than happy to bring to the floor one of our corporate members, one of more passionate corporate members, Aldo Gutierrez from EXFO. Please tell us about the multitude of solutions you provide for PIC and module testing.
Well, hello everyone. My name is Aldo Gutierrez. I'm Business Development Manager at EXFO. So today I'm excited to present the EXFO PIC testing solution. It's a comprehensive ecosystem designed to streamline the characterization of photonic integrated circuits. This solution includes the Opal automated probe station, state-of-the-art test equipment, and the pilot software platform. So let's start with the Opal automated station. So this station is built around a motorized positioning stage with thermal control, ensuring precise and stable measurements. It features a high-resolution top vision system and a telecentric side vision system, providing accurate alignment and inspection capabilities. The Opal station can accommodate up to 4 probing heads for both optical and electrical probes, offering high flexibility for various testing needs. Depending on the model, the Opal product line supports wafer, multi-die, or single-die testing. All models are compatible with surface and edge coupling, including trench edge coupling technique for wafers. Next, the test equipment relies on the CTP10 and the tunable laser product lines to perform comprehensive PIC characterization. These tools measure critical parameters such as insertion loss, return loss, polarization-dependent loss, and photo current. Operating within the telecom bands from 1240 nanometers all the way up to 1680 nanometers, These instruments sweep wavelengths at a high speed of 200 nanometer per second with exceptional spectral resolution up to 20 femtometer. This high performance makes it ideal for tasks such as microring resonator characterization. Finally, the pilot software platforms ties everything together by orchestrating the complete flow of peak characterization. It handles test preparation, executes fully automated navigation, alignment, and measurements at a high throughput. It also manages analysis and data of results. With Pilot, you can ensure efficient and accurate testing, increasing the efficiency of your peak development process. So in summary, the EXFO peak testing solution combines advanced hardware and software to deliver a seamless and high-performance testing experience. Whether you're working with wafers, multi-die, or single-die tests, this solution is designed to meet your needs with precision and efficiency. Thank you for your attention.
Thank you for your presentation, and thank you for being with us so engaged. And I know very much that we need to make an event like this one only on testing, because there are so many things to discuss, especially on the standardized solutions for testing. I see that Philip got really happy with what I just said. Let's continue, and this is the final presentation of this fantastic session. We always want to keep the best for the last, because 269 of you stayed till the end. And this presentation is coming from a center that is supporting Optica like no one else. I'm talking, of course, about IMEC in Belgium. And we want to welcome Leili Shiramin, who's going to talk about recent developments on volume manufacturing at IMEC, but most important, how they can work with all of you and what challenges they have for you. Thank you very much, Leili, for being with us. Thank you for closing the meeting in style. The floor and the attention of everyone goes to you.
So I'm Leili Shiramin, Portfolio Manager at IMEC. So I will cover the Silicon Photonics platform offering. So we are a PIC provider. That will be part of my presentation, but also ongoing development that will include the heterogeneous integration and also the work that we have started in the packaging side. So looking to the short-reach interconnect landscapes, we look at to the edge bandwidth density and energy efficiency versus the interconnect distance. We see that for the optical, with optical interconnects, we can cover quite a longer distance. While these are distance agnostic, they are performance limited. Together, in this regime, we can cover 800G or even 1.6 T products, but we always want to push toward the left side and upper side of the graph, means toward shorter interconnection. In IMEC platform, in 200 platform, we have quite some number of components that it can start from simple spiral waveguides here in the middle of the image. Last year we have in OFC, we have shown the 32 channel WDM filters. This is the results that we have done. We have achieved in 300 platform, but the design is compatible with 200 as well. Then other components, passive devices, silicon nitride, LPCVD, silicon nitride, PCVD, then vertical grating couplers or edge couplers for horizontal coupling. In the active devices, we have germanium photodiode, high-speed photodiodes, and silicon-based modulators or germanium silicon EAMs for the transmitter side, all working up to 56 gigabit per second. So this can enable 800G or even 1.6 T pluggable optics products. Looking further, a bit more detail in the platform, we have started with IC 50G, and then it was the basic devices that I mentioned. Moving forward, we added other functionality like PCVD silicon nitride, U-cut, for efficient heaters. And more recent platform is ISIP 200N that we have added LPCVD silicon nitride for CWDM filter or low loss waveguide or low loss edge couplers. This platform in combination with high speed germanium photodetector is under development, but for low speed photodetector it is already available. So they are looking to roadmap and making connection with the technology and also the 100G or 200G per lane roadmap that we have put it here. Our technology can provide up to this step, but for going further, 3.2T and means 400G per lane application that will require new material integration in the platform. So those that I showed you, they are basics, but we need to add new materials like LNO, lithium niobate, or in the detector side 3.5 devices, or TSV for the in the 3D stacking. So we see that this heterogeneous integration, it is in the critical path for realization of 400G products, and today we are busy with integration method selection and also supply chain enablement. So that means in this graph we are bringing this blue tail of the graph a bit in the higher side, higher edge bandwidth density. We are making it efficient, energy efficient, and also going toward the shorter distances. However, it is under development, and it is something that we need to tackle quite some challenges to reach to that point. How we are doing this? It is using transfer printing technology that we are taking small pieces of material, lithium niobate, from source wafer to and transfer to the target wafer. We have shown that in the proof of concept phase, we have demonstrated lithium niobate modulators integrated on ISIP 200 platform, working with bandwidth of more than 55 gigahertz. And I diagram that we have measured is 70 gigabit per second. So this is good results, but there is room also for improvement. We are working on the design optimization and also processing optimization to go toward higher bandwidths, because lithium niobate on its own, it is quite enabler material, and in pure lithium niobate platform, it can go beyond 100 gigahertz bandwidths. So that was the new developments that we are doing in the platform side, but also we have seen requests that from customers, they want to go beyond one step beyond the only silicon photonics die testing. That means we need to add some functionalities, some features around the die to make it more robust in terms of testing, and also it is one step further toward the full packaging. Of course, it is something that we have started recently together with PICs, that we are working on this. It is starting. It has been started with basic devices in the platform on the silicon edge couplers, silicon nitride U-cut edge couplers, also silicon grating couplers that we have designed based on fixed design guideline, and also assembly design kit from them. We have designed a specific test sites that we are going to put in this characterization package of PICs. Key parameters that we need to monitor for edge couplers are the insertion loss and grating couplers, insertion loss and peak wavelengths and optical bandwidth that we need to monitor to ideally keep as close as possible to the die level and wafer level performance before packaging. So this is an ongoing development, and we are working with FICS to make it happen. And ultimately, this we need to make it a bit more mature to include as part of offering to our customers. Yeah, that's
Thank
it
you.
from my side.
Thank you very much, Laili. Thank you so much. And it's so great to have Exceleprint, Kevin in the room. Happy to you want to know more about this fantastic technology, microtransfer printing, please contact Kevin, contact Laili, because this technology can really revolutionize heterogeneous integration. But the question is very clear, and Milan Milosevic from FICS is asking the right question. When do you expect to have a fully developed and qualified microtransfer printing process? And I will add at wafer level.
Yeah, so we are working on that toward making a path available for production. Today it is not closed yet. I don't have immediately answer for that, but indeed today it is in proof of concept phase, and that itself has its own challenges to tackle. But we are in parallel working toward preparing supply chain and making a production path ready for that technology also. It is a discussion that we are doing with different companies, but today that discussion is not closed yet.
You know what is closed? What is closed is the meeting, because we are 16 minutes after the time, and I would like to say that this meeting has been fantastic, fascinating. After the rollout credits, all of you who want to stay for a drink and network with each other, you can stay here in the Zoom room. For those who have to go, please feel free to go with the satisfaction of a work well done, because it was Young Pew. It was a great, great meeting. Let me say goodbye to the people in YouTube.